In this video, I'll be looking at my forward seam finder function I made to reduce and expand images using forward energy seams. At the end, we'll look at the final artifacts generated with this code. This function takes an energy map and its corresponding image as the inputs. We'll use M as our energy map variable, and this track map will be used to store our indices for our seam. We'll start by looping through each row and column of our energy map to determine the lowest energy path in the entire image. Here we look at the edge case of a pixel on the far left. Looking at the previous row, energies can only pass down from the middle and the right. Then we compute the cost function, which is the energy introduced to the system if the pixel were to be removed. This is calculated by summing the differences of intensities from new neighboring pixels. The minimum energy and cost function are summed, and the minimum value is selected and recorded along with the index from which it came from in the track map variable. This else if statement is for the other edge case, but on the right edge of the image. The else statement refers to all non-edge pixels in the image, which computes the energies and cost functions from the previous row of the pixels from the left, middle, and right. Lastly, we initialize our seam index array and traverse the track map to get all the seam points in this for loop. Then, seam index array is turned.
Here we look at the final artifacts. As you can see by comparing the red highlighted removed seams, the forward energy seam carving method carves seams much more evenly distributed across the entire image. In the bottom left corner, you see that the backward energy seam carving method takes most of the seams from the edges of the image. In the middle, you can see the comparison of how each method functioned. Clearly, the forward energy method produced a more accurate representation of the original image seen on the right.